Welcome to 30th lecture in the course of Industrial Engineering and Operations Research. In fact, we have reached midway of this course, interesting course, and we have been discussing many things about industrial engineering, and last few lectures were focused on industry 4.0, and even we discussed about industry 5.0, and I told that digital twins are going to transform our factory system, service sectors. So, we are talking digital twin means basically it is a digital replica of the real world system. So, we will discuss something about digital twin. We will conclude this topic today, and it is highly basically indicative in nature. We are not going in too much depth, but we are giving exposure. So, digital twin in particularly I will focus in manufacturing, what are the challenges and how we can achieve that. So, we can see that earlier people made that tools, okay, that means tools were used since ages. People used to have stone tools, then wooden tools and like that. Now, the tools, from tools we made to machine tools, okay. Machine tools, all machines are there, human operator is operating, but the decision is taken by the human operator. Now, people then started thinking about automating these things. So, these things have to be automated also, and then CNC machines came. So, this is what that we have been progressing day by day, and now we are going towards digital. We are having so many machines, like we are having turning, drilling, milling and electrochemical machining. So, the question comes that we have all those type of machine and they require operator to operate. So, can we replace the operator with a machine? You see that on the right hand side you are seeing a basically CO2 laser machine, which is 2.5 kilowatt CO2 laser. It is like a CNC machine. Here you can program, but even then it needs a human operator. If we can replace the human operator also, we can make use of the decision support system. Machines can learn on their own with experience, and they can have self correction ability. If there is any problem in the machine, they can repair themselves also. So, we talked about these issues are pertinent in industry 4.0, and we have already talked about industry 4.0. So, we will not talk much about that, but large scale innovation in technology pushed which the market demand pulled for a long time, leading to the emergence of German coined industry 4.0. So, basically industry 4.0 is the use of cyber physical systems for controlling machines with little human intervention, and we can also say that digital manufacturing is a part of industry 4.0. We know that the remarkable event was the invention of transistor. Today we are having very large scale integration, VLSI etc., very large scale system integration and many things, but it is due to transistors. Okay. Basically, lot of improvements have taken in transistor also, but it was invented in 1947 by John Bardeen, Walter Brattain and William Shockley at Bell Labs, and they got the Nobel Prize in Physics for that purpose. So, what do we talk about digital twin in manufacturing? Digital twin is a virtual replica of physical model or processes. It is mainly used for controlling, monitoring and evaluating the performance of the physical model or process under consideration. So, it does basically controls, it monitors and it evaluates all the things. Then real time monitoring of the manufacturing processes using digital twin enables the manufacturers to improve efficiency and throughput. The key is in the availability of data captured from sensors has made it much easier to create digital twins. So, in a sense you see that basically sensors played a very crucial part, because sensors are not there, then how you will collect the data. And sensors use lot of electronic circuits, and electronic circuits invariably use transistors, etc. That's why in the beginning I highlighted that invention of transistor. So we do the digital twin generally in 70s, etc. were used by NASA. Okay, so you can say that NASA basically started, suppose rocket is going, but you can make everything in the virtual space also, and you can get this one, and information, real time data can go to computer, and computer can send the information. We are showing digital twin, digital shadow, and digital model. So digital model is nothing but basically entire model in a computer. It is a static type of model. There is a whole machine is also available in the computer, but it doesn't have any connection with the physical model. So this is simplest thing, that is level 1 thing. But you have, suppose physical thing is this is physical thing, so we can say physical system. So digital model is not having any connection, but digital shadow is that type of thing which can take data from physical system, but it cannot do anything to that. Okay, it cannot change the physical system. So that is called digital shadow. Just like you have your own shadow, suppose you raise your hand like this, so your shadow also raises hand. But if you control your shadow, if somebody puts water on your shadow, then you will not get drenched, means it is just a shadow. So second level means one level higher to digital model is a digital shadow, where physical system can give the feedback. Suppose physical system, one shaft has broken, so in the computer also one shaft will get broken, and it will show that what will be the performance of the system, so you can know that. But digital twin is that type of thing, that highest level, that where you get a data and you can also transmit this one command. Okay, suppose shaft has broken, that information has come, shaft has broken, physical system give that signal, and then corrective action was taken and physical system was rectified. So that means it is a two-way communication. So digital twin is basically this thing. You can make something like DT, and you can have PS, and you can have two-way communication. Both ways data can transmit. Okay, so this is what digital twin. So digital model is, it is a digital representation of a physical object or a process used for design, visualization or analysis. For example, a car model, a CAD model of a car or a building. Just you have computer aided design model. Digital shadow, a digital representation that receives data from the physical system. There is no feedback from the digital to the physical system. Data flows only in one direction, only reflects the current state of the physical system, but cannot modify it. So example, educational institute bus that sends data like GPS location to cloud. So you can know that your bus has caught up in the traffic, but you cannot do anything there. You can only just get information about that system. You can see this thing. Okay, like in your screen, in your camera, you can see that where something is there. Digital twin is a bidirectional, real-time connected digital representation of a physical system. Data flows in both ways. Digital twin can simulate, analyze, and also control the physical systems. For example, a wind turbine with a digital twin that monitors its performance, predicts failures, and can adjust blade angles remotely. Now talking about model, which is the very basic things of that, as I told that model is the simplest thing. So model is the representation of the process that provides some information about it, and execution of model is called simulation. And two types of models are there, direct and inverse. Direct model means you give the input, you get the output. Inverse model means you know the output and then you guess that what must be the input. Simulation is an approximate imitation of the process, but it can be said simulation, modeling and analysis is the process of creating and experimenting with a computerized mathematical model of a physical system. And usually we do modeling with the help of FEM package, etc. that is shown here. And we can have nowadays molecular dynamic simulation and we have crystal plasticity FEM. We have already discussed about it in our previous videos. And so issues in the traditional method of modeling a manufacturing process. Suppose you are just modeling a turning process, there is a cutting tool, and but you know many things are not known properly, so you have to model it very properly, and that is what there are so many issues, and that has been discussed. We have highlighted that there are many issues in which we do not know the behavior of the material, etc. So we use machine learning algorithms because we do not know the physics of the process. So we collect a lot of data, and through data we decide that whether what is the condition of the machine that we have said. We can have, say, suppose forging operation. This is a open die forging. You are compressing that one job and it is upsetting, and you can have closed die forging, that there is die and in which you are making something like connecting rod or any object. So can we predict forging load with experience? That can be done with the help of machine learning. So there can be this type of thing that you collect that lot of data. If you model it properly, then you can simulate the forging load for different sizes. So we can have closed die forging, and we can have different type of models. Okay. So it is idea is that if you have already done the load estimation for two type of products, then if the third product is similar, then you should be able to estimate that load. Okay. And but the load estimation of course can be done by FEM also. Each time you get a new product, you can keep doing FEM, but it takes excessively computational time, and there is uncertainty about accuracy of the model, uncertainty about the input parameters. Sometimes you get this type of thing, suppose during forging, and you do not know whether it is due to numerical errors or it is physically the process shows this type of behavior. See, when I did updated Lagrangian, then I got this type of thing, but when I used early, then I did not get this type of bump there. So this is so machine learning, we have already told about that. Machine learning etc. can help in making the digital twin, because digital twin essentially needs a model also, and modeling can be done not only by FEM but also by machine learning. Machine learning is the field of study that gives computers the ability to learn on their own. And then we can model machining process, and we also discuss about smart manufacturing, that you can have here cloud, big data, machine learning algorithms are there, and then this is something you can say intangible world, and then you have tangible world, that where actually your machines are there at location 1, there are say these 3 machines, location B also they are there, and they are wireless communication among the machines is taking place, and also the information is going to internet. So this is a tangible world. So this is basically a pictorial diagram of smart manufacturing system. And then lot of data can be stored in data bank, and that can be put at one centralized location, and whenever there is a need we can access that. So it is like a cloud server, just like with cloud everybody can take water and they carry to different places, but the thing is that that's how that we can take there. And then we can have in the cloud data can be stored from various factories, and then we can use that. We have already discussed, but we have to take veracious data, that means reliable data. So we have to, unnecessary data has to be removed, it has to be improved, and more data of the similar type you get, more you get the reliability. Okay. That is the concept, that if you have got similar data, so initially if you just have one data, it may not have high reliability, but if you have got more data, so reliability increases with experience. And then you have to use some way to efficiently store the data. Some unnecessary things you have to throw it out also, so that is also there. And you have to say suppose surface roughness prediction and many type of things you have to do in machining. You have to make some model, and once the model has become reliable, then unnecessary data can be thrown. see something, if you have got many points, either you do that this thing x and y, and suppose you know this lot of x, y, lot of data you have to store, all fit some straight line, let us say, and say y is equal to mx plus c, and then you just store m and c. If it can work, that can solve your purpose, then of course there is no need to store the data. So which data can be thrown away, which data should be retained, that also has to be done. Say for example, machining is a very complex process. Of course it is very difficult to fit one model for the entire domain, but you can divide the domains also in different ranges, and in each domain you can actually put one type of model. So this type of thing can also be done. So this is one way. So in each domain you have to store only few data like that. So these type of things basically we have explained, and sometimes influential observations are evaluated using Cook's distance, and outliers are also taken care. Cook's distance is one parameter which tells whether the data will have influence or not. And then as I said that we can have on-ride optimization of machining processes that we have, and with continuous learning. And so we can have that type of scheme that suppose we have to make something, we just give that some guess point, AI basically calculates the guess parameter, and then machining is done, but we get a feedback, and then AI understands that behavior, and it can do some modification. So that type of process can go on, and usually with the help of data you can fit a neural network, like cutting speed, feed depth of cut is input, what is the surface roughness, that can be output. So learning reduces the number of simulation. That suppose your AI module initially it takes maybe 5 trials before it can make proper product, but as AI model gets trained, then it will take only maybe 1 trial and it can do prediction. We can of course make the fuzzy set based optimization also, that because a lot of uncertainties are there. So just like human being, we can say in terms of the language, and we can make that. And we need to model. We have already emphasized the importance of modeling. There are many things have to be found, and models are analytical, numerical and empirical, like data based. There are uncertainties associated with the processes like metal forging. So suppose you are doing forging, so flow stress may not be known properly and friction condition may not be known properly. So you can make a proper some relation P is equal to Cp sigma 0 Ap, but then Cp is a constant which is dependent on many other factors. So we say complexity factor, and we can adjust that. So we can estimate the forging load using cloud database, that you have got a lot of database. Factory is actually doing that some job like forging operation, but it gives the feedback gets stored in the cloud system, and then the cloud system takes appropriate decision, and then it does that. So we have done some work in that direction, that you know that one PhD student Chatterjee, he did some work on that, that models, developing model for the forging process, and which can do some approximation. So this is shown here. So we have, suppose we have got different products, and we have got closed die forged product 2, and based on those you can predict the load for a new situation. So these results are there, we will not discuss that much. And even lubricated and non-lubricated, in lubricated cases what was the data, sometimes you just give the data for lubricated case, and it can know AI system that for non-lubricated it will be how much, it will be slightly more only. But challenges associated with finding out the empirical formula, that given any new shape, is it possible to suggest a suitable complexity factor, and how do we know that two products are similar. So we can make use of the hybrid computational techniques, that FEM is there, and then neural network is also there. Both the things work together, and FEM based neural network modeling of laser assisted bending was done, in which we collected lot of data. We did some experiments also. Finally, we validated FEM model. Then lot of data was simulated from FEM, and FEM data was, because FEM takes more time, maybe 2 hours to do one simulation, then that data was used to train a neural network. The neural network predicted it very fast. Nowadays, we are talking about physics informed neural networks to make it more efficient. So, there are some papers that you can see on physics informed neural networks, but I am not going to discuss much. FEM based neural network modeling for laser assisted bending we did, as I am telling that this is a neural network, but interesting thing is that we not only predicted that one value of the, say, something bend angle, but we also predicted the range, that is most likely estimate, high estimate and low estimate of the process. So, that means this gives us a more realistic viewpoint. That means you cannot just say that it is one value. Maybe you are more confident about the middle value, but you also have to mention that ultimately what can be the range. And then inverse modeling, of course, takes that we put the sensors, and from sensors we can take the data, and based on that we can predict about the input parameters. Then nowadays even materials modeling is also getting combined with the continuum based modeling, finite element method, etc. we do, but what happens inside the material, how the temperature affects. So, for that you have to use like time temperature transformation diagram, TTT diagram, etc., which differs from material to material, but I am telling that these things also can be integrated in FEM, and we did like that, and we predicted the hardness distribution in laser irradiated sheet. When we are doing that bending of the sheet by laser heating, then what changes occur inside the material and how the hardness gets affected, that we did model, and after that we compared it with our system. Okay, that means we compared it with simulations and with actual thing which we observed. And now there is many issues are there, that there may be noisy data. So, people make use of the Kalman filter. It is a recursive estimator that uses the feedback from previously estimated value to estimate the value of the current state from a set of noisy data. So, if there is a lot of noisy data, one can use the techniques like Kalman filter. Okay, we will not go in too much detail about the Kalman filter here, because but we want to tell that Kalman filter has been used in manufacturing. It was applied to measure the tool frank in milling operation. Mechanistic modeling was used to suggest the current state estimation. The Kalman gain was evaluated based on the observed tool frank wear. The estimation suggested by the mechanistic model was then updated based on the calculated Kalman gain. The process continued till the desired level of accuracy was achieved, and has been applied in the arena of metal forming also. Then it is shows that in Kalman filter, in iterative way, percentage error keeps on reducing, and there are many machine learning techniques, but generally random forest method is very popular. Random forest falls into the category of ensemble learning. Ensemble learning is a technique that combines the predictions made by numerous machine learning algorithms to make it more accurate when compared to individual models. So, it is combined thing. An ensemble model therefore consists of numerous machine learning models. Training samples are created from the original data set termed as bootstrap sample. Bootstrap sample indicates sampling with replacement such that each data has an equal probability of it being selected, and each sample is the same size as the original training data set. Ensemble prediction is defined as the one with the average of all the prediction being made. Okay, so you can say that, say for example, this is random forest, bootstrap sample inputs are there. So, T1 one prediction, T2 does another prediction, T3 does another prediction. All these predictions are combined, and you find out the mean of all predictions, and then you give to random forest. So random forest has been applied in manufacturing, was applied in CNC milling operation to monitor the tool frank wear. Then it was applied to predict the health condition of a 3D printer, surface roughness measurement, many such type of things. Cyber security is also very important in era of Industry 4.0. In the era of Industry 4.0, there is an increased usage of data among industries. Hence, there is an ever increasing risk of cyber attacks. So, these are the measures. Industry 4.0 mainly incorporates data captured from various sensors that are used for data driven modeling. Such data are vital for industries and need to be processed from the cyber attack. Then manufacturing processes often are centrally controlled. Any external access can cause disruption in the whole manufacturing process. So encryption is a technique that helps in preserving the data securely. One way is that encrypt the data. That means when data transmits, it's not that type of thing. It is one simple example of encryption is that when sometimes children play some game, so they speak that with the sentences, but each word will be pronounced in a reverse manner. Okay, suppose Ram is a good boy, so they will say Mara and then she and then good boy, like that. So many such type of things can be done, and then so that nobody else knows that, but when it reaches to that person, then it can de-encrypt and then it can just tell the information. Challenges of using ML for modern day industries. Following are few of the major challenges: identifying outliers, applying appropriate ML algorithms for drawing inferences to any manufacturing data. So many algorithms are there, so one can confuse, so one has to have enough knowledge. Cyber security associated while maintaining a data bank for applying ML algorithms. Many ML algorithms are considered as a black box, hence it is difficult to interpret the results obtained after applying such algorithms. Now challenges for academic researchers are that researchers have to put a lot of efforts in modeling and simulation, particularly in developing countries, as a number of companies already started selling digital twin applications. Challenge is compounded. Should the researcher focus on developing their own applications or learn the appropriate application of commercial digital twin tools? A focus on in-house development of digital twin technology requires the strength to compete with bigger companies. On the other hand, too much reliance on commercial digital twin will pose threat to efficiency, effectiveness and security. So it is best to bring this topic in the fold of manufacturing education and training. Mainly, you have to adopt some middle path. That means you can use the ready-made digital twin models, but also you have to develop on your own. So these are the basic issues, and we have discussed about this thing. So this is thank you for your kind attention. We have discussed mostly many topics of industrial engineering. Of course, we discussed about some quantitative techniques also, which can also be called as a part of operations research, like we discussed about forecasting, we discussed about inventory models. But now we will coming lectures we will focus more on the operations research subject. So there will be more mathematics from now onward, in which we will tell that we will solve some equations. But this was very much essential to create a good background, and so that you get oriented, and when we write the equations, then you can visualize in terms of the physical system. So this we will start from the next class. So thank you very much.